Hey guys, today we're going to talk about the equilibrium condition in rotational motion. Honestly, I find the equilibrium is very interesting and one of my favorite parts of physics. One reason is because they make life a little bit easier. But anyway, let's get started. So if you remember, we studied two kinds of equilibrium in translational motion. So we studied statics. Oh, change the color. We studied static equilibriums and dynamic equilibriums. Yeah. So today we'll put our microscope on static equilibrium on rotational motion. Static equilibrium and rotational motion. All right. Anyway, so just to remind ourselves, what was the equilibrium condition that we learned for translational motion? F of x equals 0 and f of y equals 0. And then just to remind you guys, everything before we started circular motion and whatnot, we refer to that as translational motion, or it can be referred to as translational motion. Anyway, so what is our new equilibrium condition for rotational motion? Well, good news for you, it's not that different from the previous condition, or the translational motion condition rather. So we're going to have the sum of forces, we have the torque, the net torque of the system equals to 0. So in rotational motion, we are thinking about the forces as well as the torques, and in translational motion, we're only thinking about the torques. Only thinking about the forces. So when thinking about the net torque equals 0, right? Remember, positive torques, a positive torque is essentially moves the system counterclockwise, whilst a negative torque will move the system clockwise. So, when thinking about it, the net torque being 0, we are basically saying that the magnitude of all the positive torques, all the counterclockwise torques, equals, but is different in sign, to the magnitude of all the clockwise torques. Thus, they'll sum to 0. All right. So I'm just gonna put it in brackets here. Counterclockwise torques and clockwise torques sum to 0. All right. This is how you think about this. They sum to 0 because they'll be the same magnitude, but they will have different signs. All right. So these conditions allow us to make simplifying assumptions. And these assumptions are best shown through a physics problem. Yes. So here's our problem. A man attempts to lift a 910 kg bucket from the ground. So that's basically 1 ton, right? How much force should the man apply, and what is the force of the beam on the pivot? So let's establish ourselves now. So we have this man trying to lift this pole. And so this bucket here, this is the bucket that weighs 1 ton, and this is the pivot. So this is a basic static equilibrium problem, because when he lifts the bucket, like I can imagine previously the bucket was just a little bit down at some theta. Then he lifted the bucket and put it in a straight line, and now it's not moving. So at this snapshot, it is a static equilibrium problem. All right. And our first step here is to decide our object of interest in trying to figure out how much force the man should apply. It's a pretty long problem, but we have to first figure out our object of interest. Here, in this case, it's going to be the beam. All right. Why is it the beam necessarily? Because it touches all the other objects in the system. All right. So I think it touches the pivot, it touches the bucket and the man. So step 2 in solving this problem is to model our object as a simple shape and add the forces acting on it. So I just modeled my beam as a rectangle, and if I add the forces, well, I'm going to have a force of the pivot right there, a weight force from the bucket, and the force of the man. So now, you might wonder as to why I have these vectors of different sizes. So this brings us to our first assumption of equilibrium motion that we can make. Yeah? So, our first assumption is, hold on, I forget our first assumption. It's gonna come. I remember it. Okay, sorry guys, apologies, I was blanking. So, forces closer to the pivot are greater in magnitude to those away from it. All right. So, and why is this? Like, why? Well, I can show this. I can show you this mathematically. I know the formula for torque is going to be F over R, and I can divide this whole equation by R, and I see that the torque is is divided by R, and my force has an inverse relationship with R. So you can see that large R, and you remember R is just the distance, right? Distance from the pivot to the point of force application. Large R is going to give us a small force, and the small r will give us a large force. All right? So, yes, and it's safe to assume that for this example only, that the torques are roughly are the same at every point on on every point on the beam. The torques are the same because we're in equilibrium. So that's a safe assumption to make. That's why this works. So FP here is drawn bigger because of the fact that it's closer to F weight, is drawn bigger in magnitude than FM because of the fact that it's closer to the pivot. All right. And here, so the pivot gives an upward force. If you're confused about that, think about it as just supporting the weight of the bucket and the man. If the pivot wasn't there, then this whole thing would just fall down. So it's definitely giving us an upward force. All right. So let's continue. So step 3, determine the distances from the pivot to where the torque acts. All right. So our pivot is over here. You see I hope you see the parallels between my simple model and the diagram. So my pivot at the last, then I got my first bucket. I don't know why it just decreased in size substantially. I'm sorry. Let me just fix that really quick. the size of the vectors matter in your AP exam, so I'm trying to be a bit more conscious of that. All right. I know I call that weight in the other side, but this is really equals to weight at the same time. So don't worry about the confusion in notation. I call this weight here, but it really is, its name is f of b, but it's equal to the weight formula. So yeah, anyway, step 3, determine the distances from the pivot to where the torque acts. So our pivot is here, and our first distance is given to us in the question. We have the distance from the pivot to the bucket is 0.5 meters. These are all in meters. And the distance from the pivot to the man is 3.6 meters. What have I done? Okay. So anyway, doesn't matter. So now we have everything we need to solve this. All right? We can use our diagram that we made to solve this whole question. So to start, we have to first analyze our forces and then analyze our torques. So we only have one direction. This is thin. Hold on. Okay, so we only have one direction here, so Fy if you like. So if I'm gonna have Fy is equal to Fm positive. If I say my positive y is up, right? Then FP is also positive, F pivot minus FB, that's F bucket, all right? F pointing down. So that's how I begin my analysis. What can I get from this information? What do I know here? Well, I'm in equilibrium, so Fy is equal to 0. Fy will be equal to 0. And I think I have enough data in my question to answer, to get FB. So I know FB is equal to weight, and weight is going to be equal to mg. And what's the mass of the bucket? The mass of the bucket is given to us is 910, and gravity is 9.8. So if I multiply these two, let's see what I get. So if I have, let's see, 910 times 9.8, it's going to be 8,918 newtons. So my equation now looks like this. 0 equals Fm plus Fp. That's pp. Fp minus 8198 newtons. All right. Okay, move on. All right. So hold on. Let me just copy and paste this. Okay. I'll just write it. Okay, so we had 0 is equal to Fm plus Fp minus 8918 newtons. All right. So now, we don't have enough information to get Fm and Fp. All right. Sad. We don't have enough information. So where can we get this information? We can get this from our equilibrium condition for torque. So let's see how many torques are acting on our system, right? If I just zoom out a little bit, or you know what? I'll just be here. Yes. So if I have my torque, my net torque, and see what torques do I have? I have the torque of the pivot, if you like, and this is pointing upwards. So anything that makes the system go clockwise will be negative, a negative torque, and any torque that makes the system go counterclockwise will be positive. So my bucket has a force as well, but it's going to be negative because it's pointing down, and that down is a counterclockwise direction. Is a clockwise direction. Apologies. So torque bucket. Then the man's pointing up. So it's going to be torque man, right? So I know my condition. My net torque should be 0. So hold on. So net torque 0. So I'm gonna have, and then now I know that my torque is FR, right? So this is going to be F pivot minus what's B? B is going to be F bucket R B, by the way. The R's are not the same, so I can't leave it all as R. Plus the man will be F man FM RM. Alright? So just I'm just plugging in the magnitudes for torque. We know the FFR, and the subscripts just indicate what object I'm referring to here, with respect to the man, of course. All right, so I'm FPRP. So this is torque at a pivot. So my R is literally 0, because how long is the distance from the pivot to the pivot? It's 0. So because the force is being applied right at the pivot, so that's 0. So now gonna have FB minus FB RB plus plus FM RM. I can take this across the equal sign. FBRB equals FMRM, right? I can divide by RM, Boop, boop, cancels out. FM. Oh, look what I have. I have a formula now for the force of the man. Boom. Derived from the torque equation. All right. I know the force of the bucket. We calculated this already. This is 8918, and I also know RB. RB is the radius, is the distance from the pivot to the point at which the force of the bucket is being applied. So it's going to be 0.85. And RM is the distance from the pivot to the man, which is going to be 3.6. All right. I'm going to calculate this. So we're going to have 918, okay, times 0.85 divided by 3.6. It's going to be about 2,105 newtons. Yeah. So that's how much. So we have found the amount of force the man should apply, 2,105 newtons. But now we still have a question to answer. What's the force of the beam on the pivot? Well, we now know what F of M is. All right, we now know what F of M is, so we can plug this back in to that equation and then solve for F of P. So I'm gonna just rewrite that equation down here. So 0 is equal to F of M plus F of P minus 1.819. All right. Then I'm gonna say 0 F of man. I just calculated that. It's gonna be 2,105 plus FP, F pivot, minus 8918. So I solve for FP is an algebra problem. 819. Take that across the equal sign. I can get minus as well. Going to be FP. And this is going to be equal to, I calculate this. It's going to be equal to 8198 minus 2105. So FP, the force of the beam on the pivot is about 6,813 newtons. So there. And that's how I want you guys to think about both solving your equilibrium problems and your non-equilibrium problems. They're pretty much the same almost. So yeah. So yeah, we found FP. I did it. So yeah. So we have one more assumption that I want to do another example just to keep this video kind of short. The next assumption that we can choose to make, that we can make really, is that we have the power to choose where our pivot is. All right. So if I have my diagram here of the, if you remember how it was of our previous problem, I told you that the pivot is going to be here. But really, because I'm in equilibrium, the pivot can be here or it can be here. All right, it doesn't matter. It will still be okay mathematically. And that's really because we're in equilibrium and the torque is the same everywhere. So wherever you put your pivot, it doesn't quite matter. So because we're in equilibrium and the torque is the same everywhere. All right. So it's ideal, all right? It's always good to put your pivot at a force you don't know a lot about. All right? Or just at a force that you're not sure how to go about it. Because if you put your pivot at that particular point where the force is being applied, that torque is going to be 0. Remember, torque is equal to Fr. So if my force is right, if my force is being applied right at the pivot, my torque is going to be 0. So yeah, anyway, that's the video. I know it's a little bit long, but I hope it was helpful, guys. And yeah, see you in class on Tuesday. We're gonna answer some equilibrium problems, and yeah, we'll see how it goes.